What if everything we thought we knew about the fabric of the universe was just the tip of the cosmic iceberg? Picture this: somewhere out there in the vast expanse of space, signals echo across the void without explanation. Invisible forces warp the very laws of physics, and entire regions of reality behave in ways that defy logic. Take the WOW signal, for instance, a mysterious radio burst detected in 1977, so intense and precise that it seemed artificial, yet its origin remains one of space's greatest unsolved puzzles. Or consider dark matter, this invisible scaffolding that holds galaxies together, outnumbering ordinary matter 5-1, yet refusing to reveal itself beyond the ghostly tug of its gravity. These aren't just quirks of the cosmos, they're screaming clues that there's so much more to uncover. Welcome to a journey where the universe itself becomes the ultimate mystery novel, and every anomaly is a page waiting to be deciphered. Across the infinite canvas of space and time, reality occasionally glitches: black holes that shouldn't exist, stars that vanish without a trace, cosmic rays with energies beyond anything our physics can explain. These aren't errors in the system, they're whispers from the edges of human understanding, hinting at forces and dimensions we've yet to imagine. Think of it like stumbling upon footprints in an empty forest. You know something left them, but what? That's the thrill of these anomalies. They don't just challenge science, they rewire our sense of wonder, pulling us deeper into the cosmic unknown. In this video, we're diving headfirst into 25 of the most jaw-dropping, mind-bending enigmas ever recorded, phenomena that stretch the limits of space, time, and even logic itself. From celestial objects that defy the laws of motion to bizarre distortions in the cosmic microwave background, each one is a detective story written in starlight. And here's the wild part: every mystery we uncover doesn't just deepen the puzzle, it reshapes what we think is possible. So whether you're a seasoned space enthusiast or just someone who loves a good cosmic riddle, buckle up. By the end of this journey, you'll see the universe not as a static stage, but as a living, breathing enigma, one that's far stranger and far more thrilling than we ever dared to dream. Out of the countless radio signals that wash over Earth from the depths of space, one stands alone, not just for its strength, but for the sheer mystery stamped across it like a cosmic exclamation point. On August 15, 1977, Ohio State University's Big Ear telescope picked up a 72-second burst of radio waves so powerful, so unnervingly precise, that astronomer Jerry Amon scrawled, "Wow." In red pen right on the printout, the signal wasn't just loud, it was targeted. It hit a frequency of 1,420 megahertz, a silent channel where natural cosmic noise fades away, a frequency scientists had long speculated might be used by other civilizations trying to shout into the void. And then, just as suddenly as it appeared, it vanished, never repeating, never explained. Decades later, the WOW signal remains astronomy's most tantalizing ghost. Imagine tuning a radio between stations and hearing a voice shout your name only once and never again. That's the spine-tingling frustration researchers face. Some argue it could have been a rogue comet's hydrogen emission, but no comet was recorded in that patch of sky. Others suggest a glinting satellite, but satellites don't transmit narrowband signals that intense. And then there's the unspoken possibility: what if it was intentional, a fleeting hello from something or someone we've yet to understand? The signal's brevity is its cruelest twist, a puzzle with just one piece, a song cut off after the first note. Every search for a repeat has come up empty, leaving us with a question mark written across the cosmos in 72 seconds of static. What makes the WOW signal so haunting isn't just its origin, it's what it represents. Like finding a single, perfect fingerprint in an abandoned room, it's proof that something extraordinary happened here. And until we catch that whisper again, it lingers as both a challenge and an invitation. the universe is playing hard to get, and the game has only just begun. If the universe were a cosmic detective story, dark matter would be the unseen suspect, leaving fingerprints everywhere but slipping through every trap set to catch it. Here's the staggering truth. Everything we can see, stars, galaxies, even our own bodies, makes up less than 5% of the cosmos. The rest, a shadowy 27%, is dark matter, an invisible glue holding galaxies together with its gravitational pull, while the remaining 68% is dark energy, a force we'll get to later. Picture a spiderweb glistening with dew. You can't see the silk threads, but the way droplets cling to them reveals their structure. That's how scientists first detected dark matter, by watching stars orbit the centers of galaxies way too fast for the visible mass to hold them in place. Without dark matter's hidden scaffolding, galaxies would spin apart like shattered chandeliers. But what is it? Leading theories point to WIMP, weakly interacting massive particles, hypothetical heavy particles that barely touch ordinary matter, passing through you right now like ghosts through walls. Then there are actions, ultra-lightweight particles so tiny they could be streaming through space like an invisible wind. Some experiments, like the Xenon project buried deep under Italy's mountains, hunt for dark matter by waiting for a single, split-second flash of light, a sign a WIMP might have nudged an atom. Others, like the Action Dark Matter experiment, listen for the faintest electromagnetic whistle actions might emit in strong magnetic fields. So far, silence. The frustration is cosmic. Dark matter's gravitational grip shapes the universe, yet it refuses to show its face. It's like hearing an orchestra play from an empty room. The music is real, but the musicians are missing. Some even wonder if we've got gravity itself wrong, that maybe dark matter doesn't exist and our equations need rewriting. But the evidence piles up. The way light bends around galaxy clusters, the cosmic microwave background's faint imprints, even the universe's large-scale structure all scream that something is out there. Until we catch it, dark matter remains the universe's ultimate cold case, a reminder that most of reality is still written in invisible ink. Imagine throwing a ball into the air, only to watch it shoot away faster and faster instead of falling back down. That's the universe right now, not just expanding, but accelerating outward at speeds that defy gravity's pull. The culprit, dark energy, the most dominant and least understood force in existence. While dark matter tugs galaxies together, dark energy does the opposite. It's tearing reality apart, stretching the cosmos into an ever colder, emptier future. Scientists stumbled onto this enigma in the late 1990s by observing distant supernovae. These dying stars, which should have dimmed with predictable regularity, appeared fainter than expected, like cosmic mile markers revealing space itself was expanding faster than anyone predicted. The shock was so profound it won researchers the Nobel Prize, flipping cosmology on its head. So what's powering this runaway expansion? Einstein's old nemesis, the cosmological constant, has resurfaced as a leading suspect, a sort of anti-gravity woven into space itself. Think of the vacuum of space not as empty, but as a bubbling quantum foam where particles flicker in and out of existence, generating a repulsive force. There's just one problem. When physicists crunch the numbers, theoretical predictions for this vacuum energy overshoot observations by a jaw-dropping 120 orders of magnitude. That's like calculating the weight of a grain of sand and getting an answer heavier than the entire observable universe. Some call it the worst discrepancy in science, a glaring sign we're missing something fundamental. The implications are staggering. If dark energy's push continues unchecked, distant galaxies will eventually vanish over the cosmic horizon, their light stretched beyond detectability. The universe could end not with a bang, but with a silent, icy solitude, a fate dubbed the Big Freeze. Yet there's a twist. Some theories suggest dark energy isn't constant at all, but a dynamic field that could decay or even reverse someday. Others propose extra dimensions or modifications to gravity itself. One thing's certain, dark energy isn't just a mystery, it's a countdown clock, forcing us to rewrite physics before the universe outpaces our understanding. Every second, it stretches the gap between what we know and what remains hidden in the void. The universe is unimaginably vast, 2 trillion galaxies, each with billions of stars, many harboring planets in the so-called Goldilocks zone where life could thrive. With odds like that, the cosmos should be teeming with civilizations. So where is everybody? That's the Fermi Paradox in a nutshell, the glaring contradiction between the high probability of extraterrestrial life and the deafening silence we've encountered so far. Physicist Enrico Fermi first posed the question over lunch in 1950 while discussing UFO reports, but today, armed with rovers on Mars, telescopes peering at exoplanets, and radio arrays scanning for signals, the question feels heavier than ever. One chilling answer is the Great Filter, a hypothetical barrier that prevents life from advancing to interstellar communication. It could lurk in our past, meaning the leap from simple chemistry to complex life is astronomically rare, making us cosmic lottery winners. Or worse, it might wait in our future, a self-destruction event like nuclear war or runaway AI that erases civilizations before they can spread. Every exoplanet we find without radio chatter nudges the filter's position forward, turning it into a countdown clock for humanity. Then there's the zoo hypothesis, the idea that advanced civilizations observe us like animals in a galactic nature preserve, deliberately avoiding contact until we reach some unknowable maturity. Or perhaps we're alone after all. Drake's equation, which estimates the number of detectable civilizations, hinges on variables we're still guessing at, like how often intelligence evolves. Recent exoplanet discoveries show habitable worlds are common, but if microbial life usually stalls at single cells, Earth's biosphere might be a fluke. Some solutions are even wilder. Maybe aliens communicate in ways we can't perceive using neutrino beams or quantum entanglement. Or spacefaring societies inevitably turn inward, building virtual realities so compelling they ignore the physical universe. One thing's certain, the silence isn't just eerie, it's the universe's most provocative riddle. Every dead planet we find, every empty frequency we scan, is another piece of a puzzle we're only beginning to assemble. Until that first hello comes, the Fermi Paradox remains a mirror, forcing us to confront not just the cosmos, but our own fragility in the grand scheme of things. When NASA Pioneer 10 and 11 spacecraft ventured beyond the asteroid belt in the 1970s, they carried humanity's hopes and an unsolved mystery. Mission controllers noticed something bizarre. Both probes were slowing down slightly more than physics predicted, as if an invisible hand were tugging them backward toward the sun. This tiny deviation, just enough to shift their positions by hundreds of thousands of miles over decades, became known as the Pioneer Anomaly, a glitch in the cosmic code that left scientists scratching their heads. At first, some dared to wonder if Newton's laws needed rewriting. Could there be an undiscovered force at play, some exotic gravitational effect only noticeable in the deep reaches of space? Others speculated about dark matter's invisible influence or even flaws in Einstein's relativity, but the truth turned out to be far more mundane yet no less fascinating. Years of painstaking analysis revealed that heat radiating unevenly from the probe's plutonium power systems was pushing back on them like a faint solar breeze, a phenomenon called thermal radiation pressure. The spacecraft, it seemed, were literally slowing themselves down by glowing in the dark. Yet the story doesn't end there. Even after accounting for this thermal push, a whisper of the anomaly lingered, a discrepancy so small it could have been measurement error, yet tantalizing enough to keep the debate alive. That's the thing about cosmic puzzles. Sometimes the answers reveal deeper layers of questions. The Pioneer Anomaly forced scientists to confront how even the tiniest unaccounted forces, heat, light, even the pressure of cosmic dust, can snowball into major mysteries over astronomical distances. It's a reminder that space exploration isn't just about reaching new worlds, but about refining our understanding of the rules that govern them. Every anomaly, no matter how small, is a chance to peel back another layer of the universe's secrets. There's a hidden pattern in the afterglow of the Big Bang, and it has cosmologists whispering about a possible rewrite of the universe's rulebook. When scientists mapped the cosmic microwave background, the faint echo of radiation left over from the universe's infancy, they expected chaos, a random splatter of hot and cold spots like static on an old television. Instead, they found something unsettling. The fluctuations weren't just uneven, they were aligned along a specific axis, as if the universe had a hidden equator. Dubbed the axis of evil by researchers half joking about its threat to standard cosmology, this eerie alignment defies the cosmological principle, the bedrock idea that the universe should look roughly the same in all directions. So how strange is this? Imagine tossing confetti in the air only to watch it land in perfect parallel lines. The odds of such alignment happening by chance in a truly random universe are less than 1%, prompting some to call it the most significant anomaly in modern cosmology. Skeptics argue it could be instrumental error or foreground interference from our own galaxy's dust. But even after painstaking corrections, the axis persists like a stubborn scratch across the lens of reality. Others wonder if we're seeing artifacts of quantum gravity effects from the universe's first moments, or even more radically, evidence of a pre-Big Bang structure imprinting itself on creation. The implications are seismic. If not a fluke, the axis of evil suggests the universe has a preferred direction, a cosmic north that would dethrone relativity's assumption that no point in space is special. Some theories propose our universe collided with another bubble universe in the multiverse, leaving a gravitational bruise. Others speculate about primordial magnetic fields or defects in spacetime itself. What makes this mystery so gripping is its scale. We're not talking about a quirk in some distant galaxy, but a potential fingerprint on the entire observable universe. Until we crack it, the axis stands as both a warning and an invitation, proof that even our deepest cosmological truths might just be placeholders for revelations yet to come. In the silent void between galaxies, sudden bursts of radio waves flash into existence, brief, intense, and packing more energy than the sun emits in days. These are fast radio bursts, or FRB, cosmic strobe lights that flare for mere milliseconds before vanishing, leaving astronomers scrambling to decode their origins. Since the first FRB was discovered in 2007, buried in archival data from Australia's Parkes Observatory, scientists have catalogued hundreds of these eruptions, each one a puzzle wrapped in static. Some burst once and never repeat, like a gunshot echoing across the cosmos. Others, like the infamous FRB 121102, flicker on and off in unpredictable patterns, teasing researchers with the possibility of a pattern. What could possibly generate such staggering energy in such a fleeting instant? Magnetar's neutron stars with magnetic fields 1 trillion times stronger than Earth's are prime suspects. Picture a star so dense it warps spacetime, its crust occasionally cracking under magnetic strain, releasing eruptions of radiation detectable across billions of light years. In 2020, astronomers caught a magnetar in our own galaxy firing off an FRB-like burst, lending weight to this theory. But FRB 121102 complicates things. Not only does it repeat, but it's been traced back to a dwarf galaxy 3 billion light-years away, a chaotic stellar nursery where extreme astrophysics runs wild. Some speculate it might originate near a supermassive black hole where the surrounding plasma acts like a cosmic lens, amplifying the signal. Then there's the wild card: could some FRBs be artificial? The narrowband nature of certain bursts, especially those with downward drifting frequencies, has drawn comparisons to engineered signals. While most scientists dismiss extraterrestrial origins, the sheer diversity of FRB behaviors keeps the door open for surprises. Some even theorize they could be power beams from alien light sails, though no evidence supports this beyond imagination's reach. What makes FRBs so thrilling isn't just their mystery, it's their utility. Like interstellar lighthouses, their signals scatter through the cosmic web, revealing the invisible gas between galaxies. Each burst is a forensic snapshot of the universe's hidden scaffolding. Yet for all we've learned, fundamental questions remain. Why do some repeat while others don't? What creates their staggering energies? And are we witnessing one phenomenon or many in disguise? Every new detection peels back another layer, proving that even the briefest cosmic events can leave the longest shadows. Somewhere beyond the local group of galaxies, past the swirling arms of the Milky Way, an invisible force is reeling us in. The Great Attractor, a gravitational anomaly so powerful it's dragging entire clusters of galaxies toward it at over 600 kilometers per second, remains one of cosmology's most tantalizing blind spots. For decades, its true nature was obscured by the zone of avoidance, a region of sky where the Milky Way's own dust and stars block our view like a cosmic curtain. But recent infrared surveys have begun pulling back that veil, revealing hints of something colossal lurking in the shadows. What makes this mystery so gripping is the scale of its influence. The Milky Way, Andromeda, and hundreds of other galaxies are all caught in the same relentless current, as if the universe itself were tipping toward some unseen drain. Early X-ray observations suggested the Norma cluster, a dense knot of galaxies 400 million light-years away, might be the culprit, but its gravity alone couldn't account for the staggering pull. Then came the discovery of the Vela supercluster, a vast galactic metropolis previously hidden behind the zone's glare, which added critical mass to the equation. Yet even these combined structures seem insufficient to explain the motion. The leading theory, the Great Attractor, might not be a single object at all, but the foothills of something far larger. The Laniakea supercluster, a sprawling web of galaxies spanning 500 million light-years, with our Milky Way clinging to its distant fringe. Picture standing at the edge of a waterfall, feeling the tug of the cascade before you see it. That's our position in Laniakea's gravitational watershed. But infrared eyes like those aboard the Spitzer Space Telescope have spotted even more. Filaments of dark matter threading through the void, potentially funneling galaxies toward denser regions like cosmic rivers. Here's where it gets stranger. Some researchers speculate the Great Attractor could be a fluke, a temporary alignment of mass that'll dissipate as the universe expands. Others wonder if we're seeing the fingerprints of a larger, undiscovered structure beyond current observational limits. Every new infrared or radio survey peels back another layer, turning what was once a frustrating blind spot into a frontier of discovery. The Great Attractor isn't just pulling galaxies, it's pulling our curiosity, forcing us to question whether we're seeing the full picture or just the faintest outline of a truth still hidden in the dark. Most stars flicker gently, their light dimming by a fraction when planets pass in front. But then there's KIC 8462852, better known as Tabby's star, a cosmic oddity that doesn't just flicker, it plummets. Located 1,500 light-years away in the constellation Cygnus, this sun-like star first grabbed headlines in 2015 when astronomers noticed its light dropping by up to 22% in chaotic, asymmetrical dips, like someone repeatedly turning a cosmic dimmer switch at random. These weren't the neat, periodic shadows of orbiting planets. This was something far stranger, sparking speculation that bordered on science fiction. Could we be seeing the shadows of an alien megastructure, like a Dyson swarm of energy collecting panels encircling the star? The natural explanations are just as fascinating. One leading theory points to colossal clouds of dust, possibly from the disintegration of a moon or planet, creating an irregular debris field that orbits the star in clumps. Observations in 2018 revealed the star dimming more in blue light than red, a telltale sign of fine dust particles scattering shorter wavelengths, much like Earth's atmosphere turns sunsets crimson. Another idea involves a family of giant comets, hundreds of times larger than Halley's Comet, trailing enough gas and dust to blot out starlight in erratic bursts. Yet even these scenarios strain credulity, requiring an implausible number of coincidental disruptions to explain the star's long-term dimming trend, an overall brightness decline of nearly 3% per century, as if the star is slowly being veiled. What makes Tabby's star so compelling isn't just the what but the why now. Of all the stars in the Milky Way, why is this one behaving so dramatically during the tiny sliver of time humans have been watching? Some suggest we're witnessing a rare cosmic event, a planetary collision, perhaps, or a young star's volatile phase. Others ponder whether the star's oddities are magnified by perspective, with interstellar dust drifting through our line of sight like fog distorting a street lamp. Then there's the lingering allure of the megastructure hypothesis, a reminder that the universe might still harbor surprises beyond our imagination. For now, Tabby's star remains a riddle wrapped in a mystery. Every new observation peels back another layer, yet the core question lingers. Are we seeing a natural process so extraordinary it challenges our understanding of stellar behavior, or something even more profound? In the grand detective story of the cosmos, this star is the case that keeps defying easy answers, proving once again that reality's strangest twists often outshine fiction. The Moon today is a quiet, airless world, devoid of global magnetic fields, yet its ancient rocks tell a different story. Locked within lunar samples brought back by Apollo astronauts are traces of a staggering secret. Billions of years ago, the Moon generated a magnetic field as strong as Earth. This shouldn't be possible. Planetary dynamos, the churning cores that create magnetic fields, require intense heat and movement, something a body as small as the Moon should have lost eons ago. Picture a campfire dwindling to embers. Small objects cool faster than large ones. Mars, twice the Moon's size, lost its magnetic field early. So how did our tiny neighbor stay magnetically alive for over 1 billion years? Scientists call this the lunar dynamo problem, and it's flipped planetary science on its head. One radical theory suggests the Moon's core was once stirred by an orbital tango with Earth. Early in its history, the Moon may have orbited much closer, its mantle stretched and heated by Earth's gravity like taffy in a cosmic pool. This tidal friction could have supercharged its core, powering a dynamo long after its size should have allowed. Another idea points to colossal impacts, moonquakes from asteroids or even a long-lost second moon slamming into the surface, violently shaking the core like a snow globe and reigniting its magnetic engine. Here's where it gets stranger. Some lunar rocks hint at multiple magnetic field reversals, flip-flops in polarity that mirror Earth's own geomagnetic dance. If confirmed, this would mean the Moon's dynamo wasn't just a fleeting spark, but a complex, evolving system. The implications stretch beyond our satellite. If small bodies can sustain magnetic fields through exotic mechanisms, exomoons around distant gas giants previously dismissed as magnetically dead might harbor unseen protections for potential life. Yet the Moon guards its secrets closely. Recent simulations suggest precession, a wobble in the Moon's spin axis, could have churned its core like a centrifuge, sustaining the dynamo without requiring extreme heat. Others argue for a chemical boost, crystallization of an inner core releasing buoyant light elements, stirring molten metal like a planetary lava lamp. Every Apollo sample analyzed adds another clue, but the case remains wide open. The Moon's magnetic past isn't just a lunar mystery, it's a challenge to our very understanding of how small worlds evolve. If something this fundamental can hide in plain sight, what else have we missed in the cosmic shadows? High above Earth, hidden in the chaos of orbiting debris, conspiracy theorists claim something impossible lurks. an alien artifact watching us for millennia. They call it the Black Knight satellite, a shadowy object supposedly detected by Nikola Tesla in 1899, photographed by the U.S. military in the 1960s and still circling us today. The stories paint it as everything from an extraterrestrial relay station to a 13,000-year-old Atlantean probe. But peel back the layers and you'll find a fascinating case study in how myths take root in the gaps of human knowledge. The so-called evidence begins with radio signals. Tesla did record odd repetitive pulses in his Colorado Springs experiments, but these were almost certainly natural phenomena, perhaps the crackle of distant pulsars or the hiss of Jupiter's magnetosphere. Then there's the famous 1960 photo of a dark, angular shape near Earth, often cited as the Black Knight's first sighting. In reality, it was a thermal blanket lost during a 1998 International Space Station assembly flight, tumbling in sunlight, a mundane piece of space junk mislabeled and repurposed by eager mythmakers. What makes this legend so persistent isn't just the allure of ancient aliens, it's how space debris behavior feeds the mystery. Objects in low Earth orbit follow predictable paths, but sunlight pressure and atmospheric drag can make them appear to accelerate or change direction erratically. To the untrained eye, a tumbling panel might seem to maneuver deliberately. Even legitimate anomalies like the unidentified object tracked by the U.S. Navy's Space Command in 1998 and nicknamed the Black Knight by engineers turned out to be a fragment from a Delta rocket launch. Here's the twist: while the Black Knight isn't some interstellar scout, the truth about Earth's orbital graveyard is just as compelling. Over 29,000 trackable fragments larger than 10 centimeters currently zip around our planet at 7 kilometers per second. Dead satellites, spent boosters, even a lost glove from the Gemini era. This real-life space flotsam poses genuine risks to astronauts and satellites, yet its occasional strangeness keeps igniting imaginations. The next time someone claims to spot the Black Knight, remember, sometimes the most extraordinary stories grow from the most ordinary debris, proof that in the vast silence of space, we still can't resist hearing whispers of the impossible. In October 2017, astronomers spotted something streaking through our solar system that shattered all expectations. An object moving so fast it couldn't be bound by the sun's gravity. Named Oumuamua, Hawaiian for scout, this interstellar visitor was the first confirmed traveler from another star system, and it brought with it a cascade of mysteries. Its speed alone was staggering 87 kilometers per second as it swung past the sun, but what happened next defied explanation. Instead of slowing as expected under gravity's pull, Oumuamua sped up as if propelled by an unseen force. Theories scramble to explain this anomalous acceleration. One camp points to outgassing the idea that sunlight heated Oumuamua's surface, causing trapped gases to erupt like a cosmic soda can fizzing in the void. But here's the catch: telescopes detected no coma or tail, the usual fingerprints of outgassing. This led to radical proposals. Could Oumuamua be a hydrogen iceberg, a chunk of frozen molecular hydrogen evaporating invisibly in sunlight? Or perhaps a shard of nitrogen ice sheared from a Pluto-like exoplanet, leaving no dusty trail? Each explanation strains credibility, requiring exotic materials or formation processes never observed. Then there's Harvard astrophysicist Avi Loeb's provocative hypothesis. Oumuamua wasn't a natural object at all, but an artificial light sail, a relic of extraterrestrial technology. Its bizarre shape, estimated to be 10 times longer than wide, like a cosmic cigar, and its unexpected acceleration fit predictions for a thin, reflective probe pushed by starlight. Critics argue Occam's razor favors natural origins, but Loeb counters that science must follow the evidence, however startling. After all, Oumuamua's brightness varied tenfold as it tumbled, suggesting an extremely elongated or flat shape unlike any known asteroid or comet. The debate cuts to the heart of how science confronts the unknown. Was Oumuamua a queer but natural interstellar oddity, or humanity's first brush with alien engineering? The truth may remain forever out of reach. The object is now beyond the reach of telescopes, racing toward the outer solar system. But its legacy lingers, a reminder that the cosmos still holds wonders we've yet to imagine, and that sometimes the most profound discoveries arrive unannounced, slipping past us before we even grasp their significance. One of the most pressing puzzles in modern cosmology isn't hiding in distant galaxies or buried in quantum foam. It's embedded in two sets of numbers that stubbornly refuse to agree. On one side, we have the Hubble constant, the rate at which the universe expands, meticulously calculated by studying the cosmic microwave background's faint glow. On the other, measurements from nearby supernova and pulsating stars paint a different picture. These methods should converge, but instead, they're locked in a discrepancy that's grown too large to ignore, a rift cosmologists call the Hubble tension. Depending on where you look, the universe seems to be expanding about 10% faster than it should be, as if some unseen hand is cranking up the dial on reality itself. So why does this matter? Imagine two clocks in your house, one running slightly faster than the other. At first, the difference is negligible, but over decades, they'll drift further apart until they tell entirely different stories. That's what's happening here. The cosmic microwave background, our snapshot of the infant universe, suggests an expansion rate of around 67 kilometers per second per megaparsec. Yet when astronomers measure the current universe using Cepheid variable stars, celestial lighthouses whose brightness pulses at rates tied to their true luminosity, they get values closer to 73. That gap might sound small, but in cosmology, where precision governs our understanding of time, dark energy, and the universe's ultimate fate, it's a seismic crack in the foundation. What could be causing this mismatch? One tantalizing possibility is that dark energy, the mysterious force accelerating cosmic expansion, isn't constant as Einstein's cosmological constant suggests, but evolving. Picture dark energy as a dimmer switch slowly turning up over billions of years, its repulsive push growing stronger and subtly altering the expansion rate we measure today. Others propose modifications to gravity itself, suggesting Einstein's general relativity might need tweaking on cosmic scales. There's even speculation about early dark energy, a transient burst of repulsion in the universe's first moments that could have left an imprint on the cosmic microwave background, skewing our measurements. Then there's the wild card. What if we're simply missing a piece of the cosmic puzzle? Our local region of space could be caught in a Hubble bubble, a slightly underdense area where gravity's tug is weaker, making galaxies appear to race away faster than they truly are. Or perhaps unknown systematic errors lurk in our measurements, though teams have cross-checked data relentlessly and the tension only grows. The stakes couldn't be higher. If new physics is at play, we're standing at the edge of a paradigm shift. The Hubble tension isn't just a numbers game. It's a cosmic crossroads, forcing us to ask whether our map of the universe is incomplete, or if we're glimpsing the first hints of something far more profound. Every telescope trained on this mystery brings us closer to an answer that could rewrite the rules of reality itself. For all the dazzling galaxies and glittering stars we see across the cosmos, there's something unsettling lurking in the math, a cosmic accounting error that stumped scientists for decades. The universe's ledger shows that roughly half of all ordinary matter, the baryons making up everything from planets to people, has gone missing. This isn't about dark matter or energy, but the very atoms we're made of vanishing without a trace. The discrepancy first surfaced when astronomers tallied the matter from the early universe, imprinted in the cosmic microwave background, and compared it to modern inventories of stars, gas, and dust. The numbers didn't just mismatch, they screamed that an ocean of material was hiding in plain sight. Enter the WIM, the warm-hot intergalactic medium, a theoretical fog of superheated gas threading the voids between galaxies. Picture it as the universe's plumbing system. vast, diffuse filaments of ionized oxygen and hydrogen, hotter than the sun's corona, but so thinly spread they've eluded detection for years. This isn't the cold, dense gas of nebulae, it's matter in a ghostly state, just one particle per cubic meter, glowing faintly in X-rays and ultraviolet. The challenge, spotting something that barely interacts with light, is like trying to photograph steam in a pitch-black room. The hunt for these missing baryons has turned into a cosmic detective story. Satellites like the European Space Agency's XMM Newton have begun teasing out whispers of the WIM by observing how it absorbs X-rays from distant quasars, like tracing shadows cast on a celestial lighthouse. Even more cleverly, astronomers exploit the Sunyaev-Zeldovich effect, where the WIM-hot electrons scatter light from the cosmic microwave background, leaving minuscule temperature distortions in the afterglow of the Big Bang. The latest breakthrough came from stacking thousands of galaxy pairs, amplifying the signal until the faint fingerprint of oxygen ions emerged, confirming at least some of the WIM existence. But the mystery isn't fully solved. While these techniques have begun filling the baryon budget, there's still a gap. Some matter remains unaccounted for, possibly hiding in even sparser filaments or as yet unknown states. Simulations suggest violent galactic winds from supernova might have blown baryons so far into intergalactic space they've become nearly invisible. Others speculate about primordial black holes or exotic phases of quark-gluon plasma lingering from the universe's birth. What makes this puzzle so vital is its universality. These missing baryons aren't just cosmic trivia. They're the very fabric of reality, the unobserved threads weaving together everything we see. Until every atom is accounted for, our map of the universe remains frustratingly incomplete. A reminder that sometimes the biggest secrets aren't in the stars, but in the seemingly empty spaces between them. Deep in the constellation Boötes, there's a patch of sky so eerily empty it defies the universe's usual crowded chaos. Stretching 330 million light-years across, a volume large enough to swallow thousands of galaxies whole. The Boötes void is one of the greatest cosmic deserts ever discovered. To put that in perspective, if the Milky Way sat at its center, we wouldn't have found another galaxy until the 1960s. This staggering emptiness, often called the Great Nothing, isn't just unusual, it's a direct challenge to our understanding of how matter clusters in the cosmos. When astronomers first mapped the void in the 1980s, they expected to find at least 2,000 galaxies based on the universe's average density. Instead, they counted fewer than 60, a ghost town where a metropolis should be. The question isn't just why it's empty, but how it stayed that way. According to standard cosmology, the Big Bang's tiny quantum fluctuations should have seeded matter relatively evenly, with only modest variations. The Boötes void isn't modest, it's a cosmic sinkhole, a region where the rules of structure seem broken. One leading theory suggests the void is a fossil from the universe's infancy, a relic of an ultra-rare density fluctuation that never got filled in. Picture blowing up a balloon with a single patch that refuses to stretch, while the rest of the cosmos inflated into a web of galaxies. This pocket remained stubbornly sparse. Others propose a more violent origin. Supervoids like Boötes might be the scars of ancient collisions between bubble universes in the multiverse, where the energy of impact vaporized matter like dew in a flame. Yet even these explanations struggle with the void scale. Computer simulations struggle to grow voids this large without invoking exotic physics. Some models hint that dark energy's repulsive force might be accelerating the void's expansion, pushing galaxies away like leaves on a receding tide. Then there's the eerie possibility that Boötes isn't entirely empty, just darker than we can see. Faint dwarf galaxies or rogue stars could lurk unseen, their light too dim for current telescopes. What makes the Boötes void so captivating isn't just its emptiness, it's the way it bends our cosmic perspective. Most of the universe's volume isn't galaxies or stars, but vast, silent voids like this one. We just happen to live in a crowded neighborhood, giving us a skewed sense of reality. The Great Nothing is a reminder that the universe isn't just stranger than we imagine. It's stranger than we can imagine, hiding its deepest mysteries in the places we least expect to look. At Saturn's North Pole, a storm rages unlike anything else in the solar system. Not a swirling vortex or a chaotic tempest, but a near-perfect hexagon. Its 6 razor-straight sides stretching 30,000 kilometers across, large enough to swallow Earth twice over. First spotted by Voyager in the 1980s and later studied in stunning detail by Cassini, this geometric behemoth has persisted for at least 40 years, possibly much longer, defying every expectation of how fluids behave. On a planet where atmosphere should churn unpredictably, this hexagonal jet stream stands as a cosmic tattoo, etched into Saturn's sky with eerie precision. So how does nature craft such a perfect shape? The answer lies in the strange dance of fluid dynamics. Laboratory experiments suggest that when fluids rotate at different speeds, like Saturn's layered atmosphere, shear forces can sculpt stable polygonal patterns. Picture stirring a cup of tea with a spoon. The faster the inner liquid moves compared to the outer edges, the more likely sharp gradients form. On Saturn, where winds scream at 500 kilometers per hour, these gradients may lock into a hexagonal standing wave, a sort of atmospheric echo chamber where turbulence and order bizarrely balance. Computational models have recreated similar hexagons by tweaking rotation rates and viscosities, but none fully explain why Saturn's version is so freakishly long-lived or geometrically crisp. Earth offers no equivalent phenomenon, and the reasons highlight just how alien gas giants truly are. Our planet's weather is dominated by solar heating and surface friction. Mountains, oceans, and landmasses disrupt atmospheric flow, preventing the kind of uniform rotation needed for such geometric storms. Saturn, by contrast, is a fluid world with no solid surface to break the symmetry. Its atmosphere so deep and uniform that disturbances can reverberate for centuries. Even Jupiter's polar cyclones, while mesmerizing, spiral chaotically compared to Saturn's regimented hexagon. Yet mysteries linger. Why 6 sides? Simulations sometimes produce polygons with fewer or more edges, but 6 appears uniquely stable under Saturn's conditions. Some theorize the hexagon's roots trace back to the planet's deep interior, where convection currents or even a hidden dynamo might set the rhythm for the atmosphere above. Others speculate about Rossby waves, massive planetary-scale oscillations trapping energy in a harmonic resonance. The hexagon's color changes with Saturn's seasons, shifting from golden to blue as sunlight waxes and wanes, hinting at complex chemistry layered into the storm's structure. What makes this anomaly so captivating isn't just its strangeness, it's the reminder that even the most familiar physics can twist into unrecognizable forms under extreme conditions. The Saturn hexagon is a classroom in the clouds, teaching us that the universe's creativity far outstrips our imagination. Until we send another probe to stare into its geometric eye, this storm will keep its secrets, a 6-sided enigma spinning silently in the dark. Dark matter is supposed to be the universe's hidden scaffolding, the invisible glue holding galaxies together except when it isn't. Meet NGC 1052DF2, a galaxy that defies the rules by existing almost entirely without dark matter. Discovered in 2018, this ghostly collection of stars floats 65 million light-years away, its diffuse glow revealing a staggering truth. This galaxy's stars move sluggishly, as if they're barely bound by gravity at all. That shouldn't happen. In every other known galaxy, stars whip around so fast that without the extra gravitational pull of dark matter, they'd fling themselves into the void. Yet here, the math adds up neatly with just the visible stars, no dark matter required. This cosmic outlier throws a wrench into one of astronomy's bedrock assumptions. If dark matter is universal, how did this galaxy lose its share? One possibility is a violent cosmic robbery, a run-in with a larger galaxy that stripped away its dark matter like a thief in the night. Simulations show such encounters could leave behind a dark matter-free wreck, but DF2's undisturbed structure shows no scars of a recent collision. Another theory suggests it formed differently from the start, perhaps in a rare pocket of the early universe where dark matter was oddly scarce. But that raises more questions than answers. How would stars even clump together without dark matter's gravitational seeds? The real shocker is how DF2 challenges alternative theories like modified Newtonian dynamics, which argue dark matter doesn't exist at all, and that gravity simply behaves differently on galactic scales. Proponents claimed their model could explain galaxy rotations without invoking invisible matter, but DF2 is a nightmare for them. If gravity were stronger at low accelerations as predicts, DF2 stars should still orbit faster than observed. Instead, the galaxy acts like a pure Newtonian system, as if proposed tweaks to physics suddenly switched off. It's as if the universe handed scientists a riddle wrapped in a paradox, a galaxy that undermines both dark matter and its leading alternative. What makes DF2 so electrifying isn't just its defiance, it's the questions it forces us to ask. Could there be multiple paths to galaxy formation, some with dark matter and some without? Are we seeing a fluke or the first clue of a hidden diversity in cosmic architecture? Every new observation peels back another layer, revealing a universe far more complex than we ever imagined. Whether outlier or omen, this enigmatic galaxy reminds us that the cosmos still holds cards it hasn't shown, and that the boldest discoveries often come from the places we least expect. When astronomers mapped the afterglow of the Big Bang, they expected a smooth tapestry of heat-tiny fluctuations, sure, but nothing dramatic. Then they found the cold spot, a chilling anomaly in the cosmic microwave background that defies all expectations. Stretching nearly 2 billion light-years across, this region is significantly colder than its surroundings, as if someone left a cosmic freezer door ajar in the fabric of space-time. The odds of such a cold patch occurring randomly, less than 1 in 50. So what could create such a frigid void in the universe's earliest light? One leading theory points to a supervoid, an enormous, underdense region of space where fewer galaxies and less matter mean less gravitational pull. As light travels through a void, it loses energy climbing out of the gravitational well, a phenomenon called the integrated Sachs-Wolf effect. Think of it like a cyclist pedaling uphill. They arrive at the top slower and with less energy than when they started. The problem, the cold spot's temperature drop is twice as severe as any known supervoid should produce. Even the Eridanus supervoid, a candidate lurking in the same direction, isn't nearly large or empty enough to explain the anomaly. Then there's the wild card. Could this be evidence of a collision with another universe? Some theorists propose that the cold spot is a cosmic bruise, a mark left when our universe grazed another bubble in the multiverse. In these models, the boundary between universes could sap energy from photons passing through, creating a cold imprint. It's a radical idea, but not implausible in the context of eternal inflation, where countless bubble universes continually sprout from an expanding quantum foam. Critics argue it's speculative, yet the sheer scale of the cold spot keeps the multiverse hypothesis on the table. Alternatively, the anomaly might be a statistical mirage, a fluke amplified by human pattern-seeking instincts. After all, if you roll a die enough times, you'll eventually get a string of sixes. But here's the twist. When researchers analyzed other potential cold spots across the cosmic microwave background, none matched the cold spot's intensity. This isn't just a lucky roll, it's an outlier that refuses to be ignored. What makes this mystery so gripping isn't just the what, but the so what. If the cold spot is a supervoid, it challenges our understanding of how matter clusters. If it's a multiverse signature, it rewrites cosmology's rulebook. And if it's neither, well, that might be the most exciting outcome of all, because it means the universe still has secrets we haven't even dreamed of yet. Every new observation peels back another layer, turning this patch of sky into one of astronomy's most tantalizing puzzles, one that reminds us the cosmos doesn't owe us easy answers. In the quiet hours before dawn or just after sunset, when the sky is free of the sun's glare but not yet pitch black, a faint, ethereal glow sometimes rises from the horizon, a shimmering pyramid of light stretching upward along the ecliptic plane. This is the zodiacal light, sunlight scattered by countless dust particles orbiting the sun in a vast, lens-shaped cloud. For centuries, it was considered a predictable, if beautiful, phenomenon until astronomers realized something startling. The solar system's dust disk is shining far brighter than it should be. Here's the puzzle. Based on the known population of asteroids and comets, there simply shouldn't be enough debris in the inner solar system to produce this level of reflectivity. The dust cloud is glowing with an intensity that suggests an unseen surplus of particles, as if some invisible factory is constantly replenishing it. Where is all this extra dust coming from? One leading suspect is Jupiter's influence. The gas giant's immense gravity acts like a cosmic slingshot, hurling icy comets inward from the outer solar system. As these comets approach the sun, their frozen surfaces vaporize, shedding dust in their wake. But calculations show this alone can't account for the zodiacal light's brilliance. There must be another contributor. Enter asteroid collisions. The main belt between Mars and Jupiter is a celestial demolition derby, with rocks smashing into one another at thousands of kilometers per hour. Every impact generates a spray of fine debris, some of which spirals inward toward the sun over time. Recent studies suggest these collisions might be far more frequent than we thought, or that certain types of asteroids' brittle, loosely packed rubble piles disintegrate more easily, producing disproportionate amounts of dust. Yet even this falls short of explaining the full discrepancy, leaving astronomers to wonder if something more exotic is at play. Could interstellar interlopers be part of the answer? In recent years, objects like Oumuamua and Borisov have proven that visitors from other star systems occasionally pass through our solar system. These travelers might shed dust as they're heated by the sun, adding to the zodiacal cloud. Then there's the Kuiper belt, a ring of icy bodies beyond Neptune, which could be leaking dust inward through subtle gravitational nudges. Some researchers even speculate about a previously undetected population of microcomets, small, dark objects too faint to spot but numerous enough to collectively sprinkle the inner solar system with fresh dust. The zodiacal light paradox isn't just about aesthetics, it's a forensic clue to the solar system's hidden activity. Every speck of dust is a trace of some larger event, a comet's demise, an asteroid's fragmentation, or perhaps a process we haven't yet imagined. Solving this mystery could rewrite our understanding of how debris circulates in planetary systems, both here and around other stars. For now, that ghostly glow remains a silent question mark in the twilight, reminding us that even in our own cosmic backyard, the simplest phenomena can hold the deepest secrets. The universe is constantly bombarding Earth with cosmic rays, subatomic particles racing through space at nearly the speed of light. Most are harmless protons or atomic nuclei with energies we can explain. But a rare few pack an incomprehensible punch, hitting energies 1,000,000 times greater than anything our most powerful particle accelerators can produce. These ultra-high-energy cosmic rays shouldn't exist. Not because nature can't create them, but because they should have been obliterated long before reaching us. This is the Greisen-Zatsepin-Kuzmin, or GZK, paradox, a cosmic riddle that's had physicists scratching their heads for decades. According to well-established physics, particles with these extreme energies should collide with photons from the cosmic microwave background, the afterglow of the Big Bang, losing momentum over distances greater than 150 million light-years. It's like trying to sprint through a hail of bullets. Sooner or later, something's going to knock you off course. Yet we've detected cosmic rays that must have traveled billions of light years, arriving with energy so high they defy this inevitable slowdown. So how are they making it here unscathed? One possibility is that our understanding of particle physics is incomplete. Some theories suggest Lorentz invariance, the principle that the laws of physics are the same for all observers, regardless of their motion, might break down at these extreme energies. If true, it would mean these particles aren't playing by the usual rules, allowing them to bypass interactions that should drain their energy. It's a radical idea, akin to saying a marathon runner could suddenly ignore the effects of wind resistance. But experiments like the Pierre-Auger Observatory, which tracks these cosmic rays, haven't yet found definitive evidence for such violations. Then there's the tantalizing prospect of nearby sources. Maybe these ultra-high-energy particles aren't coming from distant galaxies at all, but from something much closer, a hidden cosmic accelerator in our galactic backyard. Potential candidates include active galactic nuclei with jets of material spewing outward, or even more exotic phenomena like decaying supermassive dark matter particles. The problem: no known object within the GZK cutoff distance matches the energy output needed to produce these rays. Unless we've missed something colossal lurking in the void, this explanation remains speculative. Yet another theory suggests these particles aren't protons or nuclei at all, but something more exotic, like neutral particles that don't interact with the cosmic microwave background. If they're, say, ultra-high-energy neutrinos, they could traverse the universe unimpeded. But current detectors struggle to explain some of these events as neutrino interactions, leaving the door open for even wilder possibilities. The GZK paradox isn't just an academic curiosity, it's a potential window into entirely new physics. Every time one of these cosmic bullets strikes Earth's atmosphere, creating a shower of secondary particles, we're handed a clue about the extreme frontiers of our universe. Whether the answer lies in rewritten laws of physics, undiscovered cosmic powerhouses, or particles we've yet to imagine, one thing is clear: the universe still has surprises up its sleeve, and they're raining down on us from the void. Venus, shrouded in thick sulfuric clouds, has long been dismissed as a hellish wasteland until scientists peered closer and found something that shouldn't be there. Hidden in the planet's upper atmosphere, strange absorption bands in the light spectrum reveal molecules we can't yet identify, dangling like cosmic breadcrumbs toward one of the most contentious debates in astrobiology. Then came the bombshell. In 2020, researchers reported detecting phosphine, a gas that on Earth is almost exclusively produced by microbial life or industrial processes. The discovery sent shockwaves through the scientific community because in Venus's acidic, high-temperature environment, phosphine should break apart within minutes. So how is it lingering in such detectable amounts? The initial observations focused on the planet's temperate cloud deck, about 50 kilometers above the surface, where pressures and temperatures are eerily similar to Earth's lower atmosphere. Here, the spectral fingerprints of phosphine appeared not once, but across multiple independent datasets, including from the James Clerk Maxwell Telescope and the ALMA array. The implications were staggering. Could floating microbes, resilient to sulfuric acid and bathed in sunlight, be thriving in this aerial niche? Critics pounced quickly, suggesting the signal might stem from sulfur dioxide, a common Venusian gas that can mimic phosphine's spectral signature under certain conditions. Others proposed exotic volcanic or chemical processes, though no known geological activity on Venus produces phosphine at the observed levels. Then the plot thickened. Follow-up studies failed to replicate the phosphine detection with the same confidence, while original authors stood by their methods. The controversy exposed how little we understand about Venus's atmospheric chemistry. Beyond phosphine, the broader mystery of those unexplained absorption bands hints at reactions we've never documented, perhaps involving unknown sulfur allotropes or even metallic compounds suspended in the clouds. Some models suggest tiny particles of chlorides or ferric chloride could be refracting light in bizarre ways, but lab experiments struggle to recreate Venus's exact conditions. What makes this enigma so electrifying isn't just the question of life, it's the reminder that Venus, often treated as a cautionary tale of runaway greenhouse effects, might still harbor secrets defying our assumptions. From Soviet Venera probes to upcoming missions like NASA Da Vinci and ESA's Envision, each new dataset peels back another layer of this planetary onion. Whether the answer lies in extremophile organisms, exotic chemistry, or something entirely unforeseen, one thing is clear: Venus, long considered a dead end in the search for life, just became the solar system's most unexpected wildcard. Somewhere beyond Neptune's orbit, where sunlight is little more than a faint star in the perpetual twilight, the Kuiper belt suddenly ends not with a gradual fade, but with a sheer cliff. Astronomers call this the Kuiper Cliff, a boundary roughly 50 astronomical units from the Sun where the population of icy objects drops off so abruptly it's as if someone drew a line in the cosmic sand. This isn't just a minor taper in debris, it's a plunge from hundreds of known objects to virtual emptiness, a void that defies our understanding of how the solar system's outer realms should behave. The moment this was discovered, it sent shockwaves through planetary science because, according to conventional models, the Kuiper belt should extend smoothly for hundreds of dwindling slowly like the last embers of a campfire. Instead, we're left staring at a cosmic edge with no clear explanation. So what could carve such a sharp boundary into the solar system's frozen hinterlands? The most tantalizing theory points to an unseen disruptor. Planet 9, a hypothetical world up to 10 times Earth's mass, lurking hundreds of away. The gravitational influence of such a planet could shepherd Kuiper belt objects into clustered orbits while ejecting others entirely, creating a stark division between the haves and have-nots of the distant solar system. Picture a shepherd dog corralling sheep, keeping some close while chasing others away. Computer simulations show Planet 9's pull could sculpt exactly the kind of drop-off we observe, but there's a catch. Despite years of searching, no one's found definitive evidence of this phantom world. Its existence remains a beautiful mathematical possibility, a celestial ghost hiding in plain sight. Then there's the observational bias argument, the idea that the Kuiper cliff might not be real, but an illusion caused by the limitations of our telescopes. Beyond 50 objects grow exponentially fainter and their orbits slow to a crawl, making them harder to spot against the blackness of space. Could we simply be missing a hidden population of distant Kuiper belt objects? Some surveys have started peering deeper, using advanced instruments like the Subaru telescope's hyper-subprime cam, but so far the void persists. Even if some objects lurk undetected, the sheer steepness of the cliff suggests something more dramatic than mere observational gaps. Alternative explanations range from the destructive to the downright exotic. Perhaps a rogue star passed through the solar system billions of years ago, stripping away the outer Kuiper belt like a thief in the night. Or maybe the cliff marks the edge of the Sun's primordial birth cluster, a fossilized boundary from when our star formed alongside siblings in a dense stellar nursery. There's even speculation about a phase transition in the protoplanetary disk, a change in density or composition that halted planet formation beyond a certain point, leaving the outer solar system forever stunted. What makes the Kuiper cliff so enthralling isn't just the mystery, it's the reminder that our solar system story is far from complete. Every time we think we've mapped the edges, the universe reveals another layer of complexity. Whether the answer lies in an undiscovered planet, a long-vanished stellar intruder, or a fundamental gap in our models, one thing is certain: The Kuiper Cliff is more than a curiosity, it's a challenge daring us to look deeper into the dark. The sun should follow basic physics. Heat should decrease as you move away from its fiery surface, just like stepping back from a campfire. Yet its outer atmosphere, the corona, defies logic by blazing at millions of degrees, hundreds of times hotter than the visible surface below. This isn't just a minor discrepancy, it's one of the most stubborn puzzles in solar physics. Imagine if the air around a light bulb were scorching while the bulb itself stayed cool to the touch. That's the baffling reality of our star, and cracking this mystery could rewrite how we understand not just the sun, but stellar behavior across the cosmos. One leading theory points to the sun's tangled magnetic fields. These invisible lines of force twist and snap like overstretched rubber bands in a process called magnetic reconnection. When oppositely charged field lines cross and realign, they release colossal bursts of energy. Think of the spark when two live wires touch, but scaled up to solar proportions. Satellite observations have caught these nanoflares in action, tiny explosions that collectively could pump enough heat into the corona to explain its extreme temperatures. The challenge, even the most powerful flares we've measured don't quite add up to the corona's total energy budget, leaving scientists to wonder if we're missing smaller, more frequent events hidden in the noise. Then there's wave heating, a cosmic symphony of vibrations rippling through the sun's plasma. Convection currents beneath the surface generate waves, Alfvén waves, named after Nobel laureate Hans Alfvén, that race upward along magnetic field lines like vibrations along a guitar string. As these waves climb into the thinner corona, their energy concentrates, transforming into heat like ocean waves crashing onto shore. The Parker Solar Probe, diving closer to the sun than any spacecraft before, has detected these waves in action, their rhythmic pulses matching predictions. Yet skeptics note that wave energy tends to dissipate before reaching the corona's hottest regions, leaving gaps in the theory, but the plot thickens. Recent studies suggest these mechanisms might work in tandem, like a celestial tag team. Magnetic reconnection could open pathways for waves to travel deeper, while turbulence from waves might trigger more reconnection events. It's also possible we're underestimating the corona's complexity. Its plasma isn't uniform, but a dynamic soup of loops, arcs, and filaments, each with its own heating quirks. Some regions might be dominated by magnetic explosions, others by wave energy, creating a patchwork of thermal processes we're only beginning to map. What makes this enigma so captivating isn't just the academic challenge, it's the real-world stakes. The corona's heat drives the solar wind, a stream of charged particles that can disrupt satellites and power grids. Understanding how it works could revolutionize space weather forecasting. And beyond practical concerns, the mystery humbles us. Even after centuries of study, our own star still holds secrets that defy textbook explanations. Every solar probe and telescope peels back another layer, but the corona's heat remains a glowing question mark in the sky, a reminder that some of the universe's most profound truths are still hidden in plain sight. Our galaxy should be a graveyard of dead stars sparkling with the remnants of stellar explosions that light up the cosmos like fireworks. Based on star formation rates and the lifespans of massive stars, astronomers predict the Milky Way should host around 3 supernovae every century. Yet the historical record tells a different story. Over the past 1,000 years, humanity has documented barely a handful of these cataclysmic events within our galaxy, with the last unambiguous one observed in 1604. This glaring mismatch, known as the missing supernova problem, isn't just a bookkeeping error. It's a cosmic whodunit where the culprit might be hiding in plain sight. One obvious suspect is interstellar dust, those thick clouds of cosmic soot sprawling across the galactic plane. Supernova erupting behind these veils could easily go unnoticed, their light absorbed and scattered before reaching Earth. Imagine a lighthouse shrouded in fog. The beam might be blinding up close, but from a distance, it's just a faint smudge. Infrared telescopes have peered through this dust, uncovering remnants of past supernova we never saw explode, like the G1.9 plus 0.3 remnant, which likely detonated around the 19th century but left no historical record. Yet even accounting for dust's obscuring effects, the numbers still don't add up. There's a gap too wide to blame solely on cosmic clutter. Could the missing supernova hint at something stranger alternative deaths for massive stars? Some theorists suggest certain stars might collapse directly into black holes without the fanfare of a supernova, imploding silently like a building demolishing itself from within. Observations of disappearing stars where massive objects vanish without the expected explosive finale lend eerie support to this idea. Then there's the failed supernova scenario, where a star's core collapse fizzles, producing only a muted optical flicker instead of a brilliant blast. These quiet exits could be slipping past our telescopes, leaving no trace beyond a missing entry in the stellar ledger. The plot thickens when we consider our galaxy's structure. The Milky Way's spiral arms, where star formation thrives, are dynamic and chaotic. Supernova occurring in these crowded regions might be harder to spot amid the stellar noise, or their light could be drowned out by neighboring bright stars. Even the Sun's position, stuck in a quieter suburban arm, might skew our perspective, leaving whole sectors of the galaxy perpetually out of view. Perhaps the most tantalizing clue lies in neutrinos, those ghostly particles that stream unimpeded from collapsing stellar cores. In 1987, detectors on Earth caught a burst of neutrinos hours before the light from supernova 1987 reached us, proving these particles could outtrace even photons in announcing a star's death. Modern neutrino observatories keep watch for similar signals, offering a backchannel to supernova that optical telescopes might miss. Yet so far, the silence persists, deepening the mystery. The missing supernova problem isn't just about tallying explosions, it's a challenge to our understanding of stellar life cycles. Every undetected supernova represents a gap in our knowledge of how stars die, how elements are forged, and how the galaxy evolves. Whether the answer lies in dust deception, exotic stellar physics, or simply the limits of our vantage point, one thing is clear. The cosmos still holds secrets about its most spectacular finales, and the next galactic supernova might be the clue we've been waiting for. For centuries, the laws of physics have been built on a bedrock assumption. The fundamental constants of the universe are just that constant. Numbers like the speed of light, the charge of an electron, or the fine structure alpha, that delicate ratio governing electromagnetism's strength, are treated as fixed pillars of reality, unchanging since the Big Bang. But what if we've been wrong? Emerging evidence suggests these so-called constants might be drifting over time, rewriting the rules of the cosmos in ways that would send shockwaves through modern physics. The first whispers of this heresy came from distant quasars, celestial lighthouses whose light takes billions of years to reach us. When astronomers analyzed the absorption lines in this ancient light, they found something unsettling. The fine structure alpha appeared slightly smaller in the past. The discrepancy was tiny, just a few parts in a million over 10 billion years, but in precision cosmology, even a hair's breadth deviation could be revolutionary. Imagine digging up a ruler buried a century ago and discovering its inches had subtly shrunk. That's the scale of anomaly we're talking about. A shift so slight most instruments would miss it, but with implications that could unravel our understanding of everything from quantum fields to the universe's expansion. Skeptics argue these findings could stem from systematic errors, instrumental quirks, or overlooked interstellar effects. After all, measuring constants across cosmic time means peering through layers of gas, dust, and redshift, any of which might distort the signal. Yet the data persists. Independent teams using different telescopes and methods have reported similar drift, particularly when studying metal ions like iron and magnesium in quasar spectra. These elements act as cosmic thermometers. Their spectral lines shift in predictable ways if alpha changes, and the pattern isn't random. The deviations align along a preferred axis in space, dubbed the alpha dipole, as if the universe itself has a grain where physics subtly varies. The stakes couldn't be higher. If constants are in flux, entire branches of physics would need recalibration. The strength of electromagnetism dictates the behavior of atoms, the binding of molecules, even the nuclear reactions in stars. A shifting alpha could mean the early universe ran on slightly different chemistry, altering how galaxies formed or how life's building blocks emerged. Some theorists speculate dark energy might be linked to these variations of fluid whose density evolves as constants creep. Others propose radical alternatives like string theories, landscape of universes, where constants aren't fixed but settle into local values like dice landing on a table. Then there's the wild card. What if the variation isn't smooth but jerky? Quantum gravity models suggest constants might jump between discrete values during cosmic phase transitions, like a dial clicking between settings. Lab experiments with atomic clocks, the most precise timekeepers ever built, have placed tight limits on current drift, finding no changes over decades. But if the shifts occur sporadically over eons, we might be living in a quiet interval between jumps, oblivious to the quakes beneath physics' surface. Whether fluke or frontier, the debate over varying constants forces us to confront an unnerving truth. The universe's rulebook might not be as eternal as we thought. Every new observation, every refined measurement, is a test of reality's steadfastness, and a reminder that even the most fundamental truths can hide surprises in their fine print. From unexplained radio bursts echoing across billions of light years to vanishing stars and phantom galaxies, we've journeyed through 25 of the cosmos' most baffling anomalies, each one a crack in the facade of our understanding, revealing just how much we don't know. These aren't just quirks, they're cosmic breadcrumbs leading us toward truths we haven't even imagined yet. The wow signal's fleeting whisper, the Great Attractor's relentless pull, the eerie precision of Saturn's hexagon, all of them scream that the universe is stranger, wilder, and more inventive than our textbooks dare to suggest. What makes these mysteries so thrilling isn't just their oddity, but how they force science to evolve. Every anomaly is a challenge, a dare to rethink what we take for granted. Dark matter defies detection. Maybe our models of gravity need rewriting. The Hubble tension won't resolve. Perhaps dark energy isn't constant after all. Even failures like the missing supernova or the Kuiper Cliffs abrupt edge our gifts, pointing to gaps in our knowledge where breakthroughs hide. The greatest discoveries often start with someone saying, "That's not supposed to happen." And that's where you come in. The next big revelation might not come from a lab or a telescope, but from someone watching this video, connecting dots no one else has seen. Maybe you've got a theory about Oumuamua's acceleration, or a hunch about the cold spot's chilling void. Drop it in the comments. Let's turn this into a brainstorm session across the cosmos. Science isn't a monologue, it's a conversation, and every voice adds to the story. If these cosmic puzzles left you as awestruck as they did us, hit subscribe. We're just scratching the surface of the universe's weirdest wonders, and there's so much more to explore, from quantum oddities to galactic enigmas that'll make your head spin. The universe is the ultimate mystery box, and together we're peeling back the layers one anomaly at a time. Thanks for joining the hunt. Keep looking up and never stop asking.